Welcome. So we are discussing about other approaches to uncertainty. So in the last lecture, we have discussed about, so basically we are discussing about three techniques which comes under other approaches to uncertainty. And these are, yes, rule-based approach, Dempster-Sheffer theory, and fuzzy logic. Okay. So this is what we are discussing. So in the last lecture, we have discussed about rule-based approach and Dempster-Sheffer theory. So in this lecture, we'll be discussing about fuzzy logic, right? Fine. So basically, fuzzy logic is a mathematical language to express certain thing. And fuzzy logic has its own grammar. It has its own syntax, semantics, like any other language or tool for communication. Okay. So there are other languages, there are other mathematical languages also. For example, we have relational algebra, Boolean algebra, predicate logic, okay, even probability theory. All these are mathematical languages. But fuzzy logic is, so fuzzy logic, we can say that fuzzy logic is one of the new language. It's not a very conventional one. It's a very new one. So basically, fuzzy logic deals with fuzzy set. So what is a fuzzy set? So first we'll be understanding like what is a fuzzy set. Before that, let us see how this term fuzzy was coined. So the term fuzzy logic was first introduced by Lotfi Abdelizadeh in 1965. So he's fondly nicknamed as Laws. So the name fuzzy logic was actually coined by this scientist, right? So if you see the dictionary meaning of fuzzy, basically fuzzy means not clear, noisy. So we cannot say whether something is either true or false. In that case, we call it as fuzzy. So you cannot directly attribute a particular, you cannot say that X is this only. It may be partially this and it may be partially something else, right? So in that case, it is called as fuzzy. So it is not clear, it's noisy. So for example, is the picture on the slide is fuzzy? Fuzzy means is it not clear? So if you find what is the opposite of fuzzy? Opposite, the anatomy, the antonym of fuzzy is crisp. The opposite term, the antonym term of fuzzy is crisp. Crisp means something which is very clear. There is no ambiguity. We can say that the weather is hot. It is, so it is surely it is hot. It means it is crisp. So if you are unable to say whether it is hot or cold, whether it is hot or about to rain, it is partially this and partially that, then uh, such features or such data points are called as fuzzy. So so first let us try to understand the difference between the fuzzy logic and crisp logic. First, let us understand crisp logic. So for a crisp logic, the answer will be either yes or no, or true or false, nothing else. Whether something will happen or not, you'll have definite answer like either yes or no. You don't have something in between. Okay. So if you take this example, milk, water, Coke, Sprite, all these things it's a liquid. So you take any one of them, and the question is the liquid is colorless? Then you will get the answer as either yes or no, right? For milk, if the input is milk, the answer is no, it has a color. For water, the answer is yes, it is colorless. For Coke, the color is no, so on and so forth. So they don't have any, there is no ambiguity in that. So such features are called as crisp data sets, and for dealing with such features, we can use crisp logic. But when you come to fuzzy logic, for a fuzzy for a fuzzy feature, the answer will be something like this: maybe, may not be, absolutely, partially, etc. So there is no, you cannot say exactly it is yes or no. So you may have multiple degrees of what you call multiple degrees of member function. So for this member, whatever the member you are checking, for that member you can have values with of multiple degree of truthness. So so such a set or such a logic is called as fuzzy logic, right? So here is an example. Say we want to know whether a person is honest or not, right? So these are the person: Ankit, Rajesh, Santosh, Kabita, and Solomon. So how do we check whether they are honest or not? So it's not a question of checking. How do we know whether they are honest or not? So when you give some person as input, right? So these are the possible outcomes we can get. Either we can say he's extremely honest, or very honest, or honest at times, or extremely dishonest. Then accordingly we assign values. If somebody is extremely honest, then we are assigning some score for his degree of honesty. So this is the score we are assigning for his degree of honesty as 99, right? So 99 and above, we say that somebody is extremely honest. Somebody is above 75, somebody's degree of honesty is above 75 and less than 99 means, then we say that they are very honest, right? Somebody's degree of honesty is greater than or equal to 55 and less than 75 means, then we say that they are honest at times. Okay, so somebody is less than 55, we say that they are extremely dishonest, right? Or we can see this way. Okay, it's not greater than 99, greater than 76. So 76 to 99, it is extremely honest. 56 to 75, it is very honest. 36 to 55, it is honest at times. Okay, 35 and less than 35, less than or equal to 35, they are treated as extremely dishonest. So here we are not saying that somebody is. So if it is a crisp logic, we would have just said whether somebody is honest or not. Whether honesty, will say whether they are, that either they are honest or they are not honest. We might have gone this way. So if you would have dealt this way, then that is called as crisp logic. But for certain problems, we want like this. So in most of the real-time scenario, it is we are actually dealing with fuzzy set. We are not dealing with any. We are not dealing with crisp features, right? So if you want to deal with this type of scenario, then actually we need fuzzy logic to deal with this, right? So our world is better described with fuzzy logic. So these are the building blocks of fuzzy logic. The fuzzy logic includes, or a fuzzy system. The fuzzy system includes fuzzy elements. A group of fuzzy elements forms fuzzy sets. From fuzzy sets, we can create fuzzy rules. From fuzzy rules, we can infer new rules. From existing fuzzy rule, we can infer new rule, and with this we can build a fuzzy system. From this we can get some output, right? So the input goes to fuzzy. The input can either directly go to fuzzy elements or sets or rules or implications, and 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 then from the fuzzy set we can derive the output. So here is an example. Let us assume that X represents all students. Say X represents all students in the class who has registered for AA. All students in AA, right? Say S represents all good students. Now what is good? How do we measure good? Say based on some parameter we measured good. S represents all good students. So basically S is a subset of X. Okay. So here S is a subset of X, right? Okay. So S belongs to the set X. Okay. So now now we are going to derive S as a fuzzy set. So something like this. Now we are going to represent S as a fuzzy set, something like this. S is equal to S comma G, such that S belongs to X. Now what is S? What is G? S represents a particular person, and G represents his degree of goodness score. S represents a particular student, and G represents the degree of his goodness score, and S should belongs to X. Okay, that is, he should be in this class. So here we are assuming in the class A, right? So here is an example. S is equal to Rajat, comma 0.8, which means the degree of goodness of Rajat is 0.8. and Kabita 0.7. The degree of goodness score for Kabita is 0.7. Salman 0.1. The degree of goodness of Salman is 0.1. Ankit is 0.9. The degree of goodness of Ankit is 0.9. Right. So now this is a fuzzy set. For every individual, we are assigning a membership value which represents the degree of goodness. Okay. So what's the difference between a fuzzy set and a crisp set? A crisp set is represented like this: S is equal to S such that S belongs to X. Okay. So when you want to represent a crisp set, we say that S is equal to S such that S belongs to X. So X is some universe. So X is some universe. From this universe, you are taking X is some universe. From this universe, you are taking all the elements which belongs to all the elements from the X, and you are keeping it in this set, right? Whereas fuzzy set is represented something like this: F is equal to S comma mu such that S belongs to X. Okay. Whereas in case of fuzzy set, we represent like F is equal to S comma mu such that S belongs to X. Now, what is this mu? This mu represents the degree of S. This mu represents the degree of S. So to what extent it is true. Okay, so that is the degree. So what extent here it is a degree of goodness. So it can be a degree of anything, right? So basically, if you see, a fuzzy set is always an ordered pair. Here also you can see the fuzzy set is always an ordered pair. One is the actual value and another one is the degree, its degree of goodness or degree of truth, whatever it may be. Basically, it's a degree of truth. Here the truth is attributed to goodness. Okay. So we can say that a fuzzy set is an ordered pair which contains a collection of values and its degree of truth. So crisp, it's a collection of elements. That's all. Crisp set is a collection of elements, whereas fuzzy set is a collection of ordered pairs, which includes elements and its membership value. So the degree of goodness is nothing but membership value. Okay. So inclusion of an element in a crisp set is based on the strict boundary. That is whether it belongs to the set or don't belongs to the set. If it belongs to the set, we will include. Otherwise, we won't include. Okay. So inclusion of an element in a crisp set, it is based on strict boundary such that whether it belongs to the set or it does not belongs to the set. Inclusion of an element in a fuzzy set, in a fuzzy inclusion of an element S belongs to X into F is fuzzy. That is, if present, then with a degree of membership. Okay. So there is no strict boundary for fuzzy. We specify some degree of membership for fuzzy sets. Okay. So here is another important point. A crisp set is actually a fuzzy set, but a fuzzy set is not necessarily a crisp set. So we can say that all crisp sets are fuzzy sets, right? We can say that all crisp sets are fuzzy sets. You may ask how. Say for example, I have a crisp set something like this, tall, which contains the set of tall students. Okay. Say I have some names here. Say Arun, Rajesh, Ravi. Say they are tall in the set of tall. Okay. Say I have another set which says that short, set of students who are short. Okay. Say Ankit, Ranjit, say Prakash. Okay. So they are short like that. Now say that I can create a crisp set for tall. So this is a crisp set. These two are crisp set. Now I can create a fuzzy set for tall. Say I'm calling it as F tall, fuzzy of tall. Okay. Now I can say that Arun. Arun also I can keep in. Arun is already in the tall set. That's not an issue. So I can say, for example, his degree of tall. I'll give some degree of membership value, which represents the degree of his how much degree he is tall. 0.8. Okay. Say Rajesh 0.9. Okay. Say Ravi 0.7. Okay. Say Ankit. Now Ankit also I can include. That's the thing. It's not that Ankit I cannot include. Ankit also I can include. Even though Ankit is in the short set, I can include. And I can assign some value for his degree of tallness. Okay. So I can say that his degree of tallness is 0.4. So so it is a relatively low value for tall. That's it. Okay. So Ranjit, I can say that his degree of 0.45. Okay. Prakash 0.3. So this is how we represent fuzzy set. So here, if you see a fuzzy set, you cannot call a fuzzy set as a crisp set, but actually a crisp set is a fuzzy set. How? A crisp set is a fuzzy set because instead of referring this set something like this, see, a crisp set is basically a fuzzy set, because instead of writing this set tall like this, I can also write that set tall like this. Instead of saying like this, I can say that Arun comma 1, which means Arun is tall. I can also say that Rajesh comma 1, which means Rajesh is tall. Ravi comma 1, which means Ravi is tall. So 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 we can assume that a crisp set also takes a membership value, but its membership value will be either 1 or 0. That's it. Whereas in a fuzzy set, the membership value ranges from 0 to 1. So a crisp set also takes a membership value, but its membership value will be always 1 or 0. Okay. Similarly, for short also I can represent like this: Ankit comma 1, so on and so forth. Right. Okay. So now when I represent in this notation, when I'm representing in this notation, I can 1 minute. So now when you represent like this, we can also here also we can include the values from other set. Now we can say that Ankit comma 0, which means Ankit is not tall, and we can say that Ranjit comma 0, which means Ranjit is not tall, and also we can say that Prakash comma 0, which means Prakash is not tall, so on and so forth, right? So here now we are representing the crisp set in a fuzzy style. Okay, so that's what here we have said. A crisp set is a fuzzy set, but a fuzzy set is not necessarily a crisp set, right? So the point is, a fuzzy set will have pair of values, and and for each element we'll have a membership score in a fuzzy set. Okay, so here is an example. So how to decide the degree of membership of elements in a fuzzy set? So that is actually uh, so that is actually we are not discussing on that. So maybe based on experience, or based on the domain knowledge, somebody may be having that. Okay, so here is an example. Say there are various cities, and we want to know the degree of comfort. So degree of comfort of this city. So for degree of comfort, we are assigning some value. For Bangalore, we are saying the degree of comfort is 0.95. For Bombay, 0.90. For Hyderabad, 0.80. For Kharagpur, 0.01. For Madras, 0.65. For Delhi, 0.75. Something like that. Now this can be represented as a fuzzy set, right? So we can say that the set name is DOM, and we can say that Bangalore, okay, 0.95, Bombay 0.90, Hyderabad 0.80, Kharagpur 0.001, so on and so forth. Right? So this is an example of a fuzzy set. Okay, fine. Let us discuss one more example. So basically, it is a something like students' grade evaluation. Let us see like how this can be done in using a crisp way, and also let us see like how it can be done in a fuzzy style. So normally we know like how it will be done in a crisp style. It is very straightforward. Say we say that somebody is exceptional, the grade is exceptional if their marks is greater than or equal to 90. If a student's marks, say it's average mark, if a student's average mark is greater than or equal to 80 and less than 90, then say it's A grade. Greater than or equal to 70, less than 80, say it's B grade. Greater than or equal to 60 and less than 70, say it's C grade. Greater than or equal to 50 and less than 60, say it is D grade. Greater than or equal to 35 and less than 50, say it is P grade, okay, less than 35, say it is F grade. F represents fail, right? Now if we want to represent using a crisp set, it is something like this. So it is very, it's a very crisp boundary. Here the boundary is very crisp. Greater than 90, greater than or equal to 90, less than 100, right? So or anything greater than or equal to 90, we call it as exceptional. Greater than or equal to 80, less than 90, A grade, so on and so forth. So this is a crisp representation. There is no, the boundaries are strict. So we can easily know, say somebody got 33, their mark is 33, then just draw a line and we know that they are in this class F. Somebody's score is 72, so it will be coming here, so you draw a line, so they are in this class, their class is B, right? Something like that. Now this can also be represented in a fuzzy way. Here you can see whatever we have discussed, the same problem is represented in a fuzzy style. Now, now we are saying that 100 is, say this point, you can say this is 82 or 83. Let us say 83. So if somebody's score is greater than or equal to 83, okay, then we are saying that they are in exceptional case with some degree. Okay, see somebody is greater than 90 means, see here what does it mean? Actually, you may ask, see this line you can see, let us take this alone. This alone you see, this point, this, let us take this cell alone. So if somebody's score is, so this is nothing but, so this line, so whatever the blue thing I have drawn, this is nothing but the membership score. This is nothing but the membership score for a given class. Now the class is exceptional. Okay, so say if somebody scored 83, then their membership score for exceptional is 0 because it is coming here, right? Say somebody scored 84, then their membership score, then their membership score for exceptional is, maybe it is somewhere here 0.1. Okay, somebody score 85, then their membership score will be here 0.2. 86 maybe 0.3. Okay, 87 maybe 0.4, 88 maybe 0.5, so on and so forth. Okay, 86.8, like that. When their mark becomes 90, if someone's score is 90, by that time their exceptional or their membership score is 1. Okay, so if somebody's score is greater than or equal to 90, so if a student's score is greater than or equal to 90 in a particular course, then they are surely in exceptional category. There is no doubt. But if somebody's score is greater than 80 and less than 90, then also they will have some membership value for the class of exceptional. Okay, they will have some membership value for the class of exceptional. Okay, at the same time they will be also having membership value of 1 for the class of A. So anything greater than 80, you can connect it here also. So if anything greater than 83 and less than 90, they already have a membership value of 1 in class A. So this can be drawn like this also. Okay, because they have a they are surely in class A, but to some degree they are also in class EX. So that is what this diagram represents. So similarly, it is applicable for all cases, right? So say for example, some student has scored the mark 72. So now if you see 72 or say 75, so if you see 75, so somewhere it is coming here. So 75, see A grade, it is coming here also. So if you draw a line here, if you draw the line actually intercepts at 2 points. One is here. This is, it is intercepting at A and it is intercepting at this point at B. Okay, so 75. So if you see 75, it has, with respect to B, okay, with respect to the class B, it has a membership value of 1. Okay, with respect to class A, it has a membership value of some membership value. It has membership value of 0.3, right? So 75 means, so the student who score 75, he comes in class A with a degree of membership value of 0.3, and he comes in also class B with a degree of membership value of 1. So that's what it represents. So if you want to represent something like this, then we should go for fuzzy way of representing, right? Okay. here are few examples of fuzzy set: high temperature, low pressure, color of the apple, sweetness of an orange, weight of mango. So high temperature means how much high? We can give some value. It is very high. So we can say that it is very high, extremely high. Okay, extremely high, high, not high. So so it is not like whether it is high or low, whether it is high or not high. No, we have these values, possible values. So for different possible options, we may have different membership scores, right? So 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 this is an example of a Z set. Similarly, for low pressure, we may have like extremely low, very low, not very low, something like this. Color of apple. So here also we can have some score, like whether it is whether it is extremely red, whether it is very red, right? Or whether it is not red, something like that. Sweetness. For sweetness also we can give some uh, give some parameters, like how much sweet it is. It is extremely sweet, it is very sweet, it is just sweet, it is not sweet. Weight. Similarly, weight also. So all these are some of the examples of uh, fuzzy data items, right? Or fuzzy sets. And the degree of membership value for fuzzy sets, it always lies between 0 and 1. So now let us try to understand some basic terminologies and notations connected with fuzzy set. Okay. So let us try to understand the membership function of a fuzzy set. If X is a universe of discourse and if X belongs to X, then a fuzzy set A in X is defined as a set of ordered pairs, that is, okay, if X is the universe of discourse, that is, we are considering the universe of discourse as X, okay, and some element X belongs to X, okay, then the fuzzy set A in X is defined as a set of ordered pairs, that is, A is equal to X comma mu A of X, such that X belongs to X, right? So we say that A is equal to X comma mu A of X, right? Such that X belongs to X, right? So where X is coming from this set X, where this mu A of X is nothing but the membership function or the membership value of X, right? So the mu A of X maps each element of X onto the membership grade, and this membership grade will take value between 0 and 1, right? So here is an example previously which we have discussed. It is similar to that. Say X represents all cities in India and A represents the city of comfort. So now A is a fuzzy set which represents the comfort of different cities. So A is equal to, we are saying that New Delhi, its degree of comfort is 0.7, Bangalore 0.9, Chennai 0.8, Hyderabad 0.6, Kolkata 0.3, Kharagpur 0. We are assigning some membership value which represents the degree of comfortness of these cities. So the membership function can take either discrete value or it can take continuous value, right? So this is an example of a discrete value. So there, say for some value of X. So here you can see, say if you number X something like this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For some value of X, the membership values are same. For 0, 1, and 2, the membership value is same. Similarly, for greater than 2, 3, 4, and 5, the membership value is this. 5, 6, and 7, this is the membership value. So this is discrete. This is an example of discrete values for membership. Okay. So basically the membership function can take either discrete value or continuous values. So it's not that it should be always discrete or it should be always continuous. Okay. So the membership can also take continuous values. So now let us try to understand certain few terminologies. The support of a fuzzy set A is the set of all points X such that X belongs to X, a set of all points X such that mu A of X is greater than 0. Right? That is, if the membership value is greater than 0, then the set of all points where the membership value is greater than 0, that is called as support. Okay. So support of a fuzzy set. A is a fuzzy set Now if you want to identify the support of A, so it is the set of all points whose membership value is greater than 0. Say for example, A is something like this. We are representing A something like this. X1. X1 is a member. Say its fuzzy score, say its membership value is 0.1. Say X2, its membership value is 0. Say X3, it is 0.7. Okay. Say X4, again it is 0. Right. Now if you want to identify support of A, as per the definition, support of A of a fuzzy set is the set of all points such that the membership value is greater than 0. Then you identify for which the membership value is greater than 0. For here, the membership value is greater than 0. For here, the membership value is greater than 0. So the support of A includes X1 because its membership value is greater than 0. It will not include X2 because the membership value is not greater than 0. And also it includes X3 because here also it's greater than 0. And it won't include X4. So this is the support of A. Okay, this is how we define the support of A. So this is diagrammatically it represented. Here it is represented. It represents all points whose membership value is greater than 0. And what is core? The core of a fuzzy set A is a set of all points in X such that the membership value is equal to 1. So wherever the membership value is exactly 1, that is called as core. Say, let us again assume A is equal to say X1 comma 0.7, say X2 comma 0.8, say X3 comma 0, say X4 comma 1, say X5 comma 0, say X6 comma 1. This is 1. Okay. Now what is core of A? Now core of A is those points where the membership value is exactly 1. So here the membership value is 1 and here the membership value is 1. There is nowhere the membership value is 1. So it is X4 and X6. This is the core. Okay. So it is diagrammatically represented like this. So a particular variable X, it takes these possible membership values. The core is this area because it takes the membership value 1. Okay. And then we define something called as normality. So when we say that a fuzzy set A is normal, a fuzzy set A is normal if its core is not empty. That's it. So what is core? So the core of a fuzzy set is the set of all points in X such that the membership value is 1. It's a set of all points such that the membership value is 1. If the core is not empty, then we say that the fuzzy set is normal. That is if a fuzzy set contains at least one value, one element with the membership value 1, then we say that it is normal. Okay. So here is an example. This diagram, if you see, actually this is not normal. Here the normality of A is false in this case because this is the membership function. Here you can see this is the x-axis which goes from 0 to 1. There is no point which goes up to 1. So this is not a normal. But if you say this case, here the normality, in this case, the normality of A will be true because there are some values which are touching 1. Okay. Even if there is one value, even if there is one membership value of 1 for a particular variable or for a particular element, then we say that it is normal. Okay. Crossover point. The next terminology we'll be discussing is crossover point. A crossover point of a fuzzy set A is a point X at which mu A of X is 0.5. So crossover point is a point at which the membership value is exactly 0.5. So because 0.5 is somewhere the midpoint. So this so for what value, for for which element you are getting the membership value as 0.5, all those points are called as crossover point. For example, if you have a fuzzy set something like this, x1 0.7, x2 0.6, x3 0.5, x4 0.4, x5 0.5. Okay. x 6.9, x 7.5. Now in this case, identify where for which elements you have a membership value of 0.5. This is not 0.5, this is not 0.5, this is 0.5. So crossover of A. So crossover of A is x3, then is not 0.4, this is 0.5, then it is x5, x3 comma x5 comma this is 0.9 comma x7, right? So it is the set of all points whose membership value is exactly equal to 0.5. Such such values or comes under crossover points, right? Then what is a fuzzy singleton? Something called as fuzzy singleton. A fuzzy singleton is defined something like this: a fuzzy set whose support is a single point in X with mu A of X is equal to 1 is called a fuzzy singleton. Okay, that is the following fuzzy set is not a fuzzy singleton. A fuzzy set whose support is a single point in X with mu A of X is equal to 1 is called a fuzzy set. Okay, so what is the support? See, if you recall, what is the support? Support represents the set of values which are greater than 0. Okay, set of points, set of elements whose membership score is greater than 0. All those represents support. Okay, so when you say that a fuzzy set as a fuzzy singleton, we call a fuzzy set as a fuzzy singleton if its support whose support is a single point in X, whose support is a single point in X such that mu A of X is equal to 1. This is not a fuzzy singleton set because here you can see there are many points which are greater than 0. All the points are greater than 0 only, and there is one point with the with the value of 1. Okay, but still this set is not called as a fuzzy singleton set. The reason is a fuzzy set whose support is a single point in X. Just a minute. Okay, so this is not a fuzzy singleton set because it's what you call its support is not its support has so many values. Its support has so many values, whereas in a fuzzy singleton set there should be only one support. A fuzzy singleton it should have only one support value, and that support value should have a membership value of 1. So that is the definition. A fuzzy set whose support is a single point in X, it should have only one point in X such that its mu A of X is equal to 1. Okay, it cannot have more than that is it should have only one point. Say for example we have something like this: A is equal to x1 comma 0, x2 comma 0, x3 comma 0, x4 comma 1. This is actually a fuzzy singleton set because if you take the support of this if you take the support of A, support of A has only one point, that is x4, and if you check the membership value of x4, that is 1. Okay, so when we call a fuzzy set as a singleton set, in the sense its support should have only one value, and that value should have a membership value of 1. Then we call it as a fuzzy singleton set. Okay. Then alpha cut and strong alpha cut. The alpha cut of a fuzzy set A is a crisp set, which is defined something like this: A alpha is equal to X such that the membership value of X is greater than or equal to alpha. Right? So it includes all all elements for which the membership value is greater than or equal to alpha. Strong alpha cut is defined something like this: A alpha dash is nothing but it is equal to X such that the membership value of X is greater than alpha. The only difference is here the membership value should be greater than or equal to alpha. Here it should be greater than alpha. Right. We can stop here with respect to our discussion on fuzzy logic. So what we are discussing is just an introduction to fuzzy logic. We are not discussing anything in detail. So fuzzy logic is also one of the technique to represent uncertainty. Okay. So let us discuss some example for A alpha and A alpha dash, that is alpha cut and strong alpha cut. Assume that there is a set A. So this set X contains these values x1 comma 0.1, x2 comma 0.3, x3 comma 0.5, x4 comma 0.7, xy comma 0.9. Okay, now if I say that A, if you say A alpha, that is strong alpha cut. Okay, let us assume alpha value as 0.3, right? So if it is A 0.3, then the set will include x2, x3, x4 and x7, because these are the elements whose membership value is greater than or equal to 0.3. x2 is 0.3, x3 is 0.5, x4 is 0.7 and x5 is 0.9. If you find out, if you want to identify strong alpha cut, that is A alpha dash, which is A 0.3 dash, which is equal to, now you should not include x2, because now strong alpha cut represents only those members whose membership values are greater than alpha. So for x3 it is greater than 0.3, so it is x3, x4 and x5. Okay, this is x5, not 7, right? So that's it. Fine, let us stop our discussion here. Thank you.